The second part of the video for this topic deals with some special cases. We introduce this thing called the Squeeze Theorem, and we show how we can use it to find a couple of limits. One of them is, fairly important. And then we see some other examples of limits that we need to be aware of. All right, so here's a fact about limits. It's known that if C is on the interval a to b, and f of x is less than or equal to g of x on that same interval, except possibly at c, right? So the functions may be undefined at those points. There may be some other special situations going on. But if it's defined everywhere else, and f of x is less than or equal to g of x on the interval, then the limit as x approaches c at f of x is less than the limit as x approaches c of g of x. That should seem intuitively reasonable. Now the Squeeze Theorem says, well, it adds on to it a little bit. Squeeze Theorem says, basically, if we can show that a function is between two other functions on some interval, except possibly at some c value, then, and we can also show that the limits of the outer functions are equal to some value L, then the limit of that inner function must also be equal to L, right? So the inner function must be squeezed between the two outer functions. All right, so what we see here is that if we can show that the h of x is between two other functions, f of x and g of x, and if we can show that the limit of f of x at x as x approaches c is L, the limit of g of x as x approaches c is also L, then the limit of that h of x as x approaches c must also be that same value L. Okay? So let's see some examples of how we can use this Squeeze Theorem. All right, so if we wanted to find the limit with x approaching 0 of x squared times sine of 1 over x. All right, so you might think, well, we have a property that a property of limits that says, hey, we can break this up. So you might say, well, let's try this. Let's write this as the limit with x approaching 0 of x squared times the limit with x approaching 0 of the sine of 1 over x. It seems reasonable. The limit with x approaching 0 of x squared, that's easy enough. That's 0. But the limit with x approaching 0 of sine of 1 over x, we saw this limit in a previous section. I think that was in the Introduction to Limits topic. For the video for that, we saw that this limit does not exist. Now, just because we have a 0 times it does not exist, that doesn't mean that this whole limit necessarily does not exist as well. What we need to do is take a different approach, right? Try a different approach to this exercise and see if it's valid. All right, so this doesn't work. Let me just kind of X through all this or delete it. All right, so we're going to try a different approach to this exercise. So here's what we're going to do. We're not going to start with this. We're not going to start with the x squared times sine of 1 over x. I'm going to start with just this part. I know from my understanding of the sine function that the sine of 1 over x must be between -1 and 1. No matter what x is, the sine of 1 over x must be between -1 and 1, as long as x is non-zero, right? So as long as x is non-zero, right? Because if x was 0, 1 over x is undefined, and we can't find that. But if x is not 0, then the sine of that 1 over x must be between -1 and 1. That's how the sine function works. If you remember the sine function, the range of the sine function is -1 to 1. All right, so now what we're going to do here is then, well, I need to get an x square sine 1 over x. And I also know that x square is greater than 0 for all x not equal to 0. So let's multiply both sides or I shouldn't say both, I should say multiply the inequality by x squared. You might say, well, why did I need that previous statement? Why do I need to know that x squared is greater than 0? Well, remember, if you have an inequality and you multiply or divide by a number that could be negative, then maybe you have to switch the symbols of inequality. So we've got to be careful about situations like that. Right? Whenever you're multiplying a number by an inequality, or an inequality by a number, you've got to be careful about the signs of that inequality. Now, since we know x squared is positive for x non-zero, and we multiply inequality by x squared, then negative x squared must be less than or equal to x squared sine 1 over x, which must be less than or equal to x squared. Now, let's look at the outer functions, right? If we have this three-part inequality, let's consider the outer functions. I know that the limit with x approaching 0 of negative x squared is 0. And I also know that the limit with x approaching 0 of x squared is also 0. Therefore, by the squeeze theorem, what do we know? Let's see, what is this telling us? We've shown that x squared sine 1 over x is between two other functions. It must be contained between negative x squared and positive x squared. And I know that the limit as x approaches 0 of each of those outer functions is 0. So by the squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x must also be equal to 0. So that's a way that we can use the squeeze theorem to prove a limit. All right, so this was a case where we could use some knowledge from trigonometry along with a little bit of algebra and this new tool of the limit and the squeeze theorem. This next example is a bit trickier, but it's an important limit. We want to find the limit as x approaches 0 of sine x over x. And I mentioned this in a previous earlier in this topic. I said this limit ends up being an indeterminate form, and we'll get to it later. Well, now it's later. So this one's tricky, and we can't use the same exact concept that we did before, unfortunately. It just doesn't work. So we actually rely on a geometric argument. And so here I've got this diagram, and what I have is I have a part of a circle here in the first quadrant. And I have this line, this ray. And here's what I'm going to say. I'm going to label this. And listen, I didn't think of this. I've learned this along my path in mathematics. And, you know, would I have been able to figure this out on my own? I don't think so. But once I saw it, I said, hey, this is pretty neat. And it's an interesting way to approach this exercise. So here's what we're going to do. We're going to define a few regions. We're going to define some areas. What I'm going to do is, I'm going to start by labeling some things. Let's think that this is part of the unit circle, so I'm going to call this point on the unit circle, this is 1, 0. And I'm going to say that this rotation right here, the angle is x. Well, then this point right here, if that's the rotation x, then this point is the ordered pair cosine x, sine x. Now, I'm going to define a couple other pieces. First, this height, right here. Well, the height must be the sine x. I'm going to define a second height, and that's the height from the ray to the point 1, 0. That vertical distance right there, let's figure that vertical distance out. So that vertical distance, we can use similar triangles because I have a right triangle here and I have a second right triangle involving the side with this unknown. Let's call this unknown z for a moment. Well, I know that this horizontal distance to the first vertical line, I know that that distance is cosine x. So then I know that the sine of x is to the cosine of x, as z, that vertical distance, is to 1, the horizontal distance. And so what we can see is then that implies then that z is tangent x. So now what I'm going to do is I'm going to make a geometric argument using these ideas. Alright, so the first thing I'm going to do is define a few shapes. The first shape is this triangle. And I have a triangle that goes along the ray, and from that point cosine x sine x connects straight to the point 1, 0, and then goes back to the origin. So I've got this circle. I'm sorry, that triangle. And so I want to find the area of that first triangle, which I've marked in red. Now in blue, I have a slightly different shape. I'm going to again go from the origin to the point cosine x sine x, but then I'm going to go along the circle to the point 1, 0. It's a little bit more, isn't it? And then back to 1, 0, or back to the origin. And so I want the area of that circular sector. And then finally, in purple, I'm going to go from the origin, I'm going to extend along the ray to this point up here, where I'm connecting with this horizontal, vertical height that I mark z, which is equal to tangent x. And so I have this other purple triangle. And I hope you can see from the drawing that the area of that red triangle must be less than or equal to the area of that circular sector in blue, which is less than the area of that purple triangle. Now, each of these areas can be found using basic geometry. The area of the triangle. Okay, well, an area of a triangle is half base times height. All right, so the red triangle, the base, all right, the base is 1 unit, and the height of that triangle is sine x. So the area of the red triangle is 1/2 times 1 times sine x. And that's less than or equal to. Now the area of a circular sector. The area of a circular sector is 1/2 times the radius times the angle. All right, so the radius is 1 and the angle is x. So in blue, that's 1/2 times 1 square times x. And then the area of the outer triangle, the purple triangle, again 1/2 base times height. That would be 1/2. The base is again 1, but now the height is tangent x. All right, so if we clean this up now, we have sine x over 2 is less than or equal to x over 2, which is less than or equal to tangent x over 2. All right, so now let's multiply through by 2 over sine x. So let's multiply the entire thing by 2 over sine x. Now, we should really be a little bit careful here because sine x can take on negative values. But since we defined x as being a positive angle, then the sine x is also positive over that interval. If we had defined x to be a negative angle, then the sine x would be negative. It would all work out well in the end. But I should at least mention that we should be careful about these things. Okay, let's continue on. So if we multiply the entire inequality by 2 over sine x, then this becomes 1 is less than or equal to x over sine x is less than or equal to, now tangent x, remember, is sine x over cosine x. So sine x over cosine x divided by sine x. So this ends up being 1 over cosine x. Okay, so now let's reciprocate the whole thing. Now, if we reciprocate each of the parts of a three-part inequality, or any inequality, it flips the symbols of an inequality. So then 1 is greater than or equal to sine x over x is greater than or equal to cosine x. So I've been able to show, using a geometric argument, that 1 is greater than or equal to sine x over x, which is greater than or equal to cosine x. Now, we wanted the limit as x approaches 0. And notice that I have the expression sine x over x. Since the limit as x approaches 0 of 1 equals 1, and the limit as x approaches 0 of cosine x is 1, by the squeeze theorem, the limit as x approaches 0 of sine x over x must also equal 1. So this limit is equal to 1. It's a fairly important limit. We're going to need it in the next unit. And so we prove it here. So now this is a tricky proof. There's no doubt about it. And again, would I have been able to come up with it on my own? Probably not. I learned it from others. And this is what we expect of you right now. We don't expect you to create new mathematics. We expect you to be able to learn the mathematics that's already been shown and be able to then demonstrate it. So what if we were asked to now find the limit with x approaching 0 of cosine x minus 1 over x? We might be able to come up with a geometric argument for this one as well, but we don't need to. So instead what we're going to do is we're going to use some trickery. Now you might say, well, hey, can we just use a direct substitution? Well, if x approaches 0, cosine x would be 1. 1 minus 1 is 0. 0 over 0 is indeterminate. So, we're going to use some trickery. Let's multiply both numerator and denominator by cosine x plus 1. I say, well, why? Why did I choose that? Well, it is a conjugate. Again, we've seen that trick with the conjugate, but there's a different reason here. Let's follow through with this and see what happens. So then this becomes the limit with x approaching 0. I've got an a minus b times an a plus b. That's a cosine square x minus 1 over x by cosine x plus 1. I might look at that numerator and say cosine square x plus 1. I've seen something like that before. In fact, I know the Pythagorean identities. I know that sine square x plus cosine square x is equal to 1. So if I manipulate this a little bit, if I want a cosine square x minus 1, let's subtract 1. Let's move the sine square x to the other side. then cosine square x minus 1 is negative sine square x. So then this becomes the limit with x approaching 0 of negative sine square x over x by cosine x plus 1. All right, now, some more trickery here. We're going to break this up. This becomes the limit with x approaching 0, and I'm going to think of it like this. Well, I can bring the negative outside, and I'm going to think of that sine square x as a sine x times a sine x over an x times a cosine x plus 1. I'm going to think of it like that. Because I know how to deal with the sine x over x as x approaches 0. We just solved that in the previous exercise. And then we'll see what happens in the other term. So then this becomes negative limit x approaching 0 sine x over x times limit x approaching 0 sine x over cosine x plus 1. All right, now, this limit goes to 0. Sorry, it does not go to 0. It goes to 1. We just proved that in the previous slide. This limit goes to 1. Let's see what happens with the second limit. If x is approaching 0, then the sine of 0 is 0 over cosine of 0 is 1. 1 plus 1 is 2. So this ends up being negative 1 times 0 over 2, which is 0. All right, so what this means is, after all that, we know that the limit with x approaching 0 of cosine x minus 1 over x is in fact 0. All right, so those are a couple special limits that we need to be aware of. That the limit with x approaching 0 of sine x over x is 1. We saw that in the previous slide. And this second limit here, the limit with x approaching 0 of cosine x minus 1 over x is 0. We're going to need both of those limits in the next unit. A couple other special limits we need to be aware of, and I can't prove these yet. It'll take some more... One of them I'll never actually prove in this course. The other one we'll be able to prove in a later topic, much later topic. But a couple limits we want to be aware of. The limit with x approaching 0 of e to the x minus 1 over x. And if we were to just try a direct substitution, that gives us an indeterminate form because e to the 0 is 1, 1 minus 1 is 0, 0 over 0 is indeterminate. But it turns out, and you can try this out on a calculator, if you try to find numerical evidence for this, you'll find that this limit is exactly 1. Another special limit we should be aware of is that the limit with x approaching 0 of 1 plus 1 over x to the x. This is another special limit. Limit as x approaches 0 of 1 plus 1 over x to the x. This is, and if you sort of think, 1 over 0, that's undefined, and we've got 1 plus an undefined expression to the 0 power. That doesn't seem like we should be able to evaluate it. It turns out to be an indeterminate form. Actually, we should say x approaches 0 from the right. We should be a little bit more careful there. This limit is actually the definition of the Euler number, e, which is approximately 2.71828. So there's a couple special limits to be aware of. All right, let's look at one more exercise here. We have this limit with x approaching 0 of sine of 6x over x. And I say, well, gosh, that looks a lot like the sine, the limit of x approaching 0 of sine of x over x. All right, so we know from previous experience, we know that the limit with x approaching 0 of sine of x over x. We know that that limit is 1, but we don't have x in the numerator. We have a 6x. So what we're going to do here is we're going to use a substitution. And this is an important concept in higher mathematics, is the idea of a substitution. So here's what I'm going to do. I'm going to make a substitution. I'm going to let u equal 6x. If u is equal to 6x, then as x approaches 0, what happens to 6x? As x approaches 0, well then 6x would approach 0. And so then that means then that u is approaching 0. And if I let u equal 6x, then that also implies then that x is dividing both sides of the equation by 6, x is u over 6. So then this limit, the limit with x approaching 0 of sine of 6x over x, this is the same then as the limit with u approaching 0 of sine u over 6. Alright, so if I'm dividing by u over 6, that's the same as multiplying by 6 over u. So then this is the same as the limit with u approaching 0 of 6 sine u over u. I can bring the 6 outside the limit. So that's 6 times the limit with u approaching 0 of sine u over u. Now if we look at this limit with u approaching 0 of sine u over u, that's the same as the limit as x approaching 0 of sine x over x. It's just a different letter, right? It's a dummy variable. The letter that we use doesn't matter. And so then this becomes then, this limit becomes 6 times 1, which is 6. Alright, so if we have some limit involving a sine of a quantity over that same variable, we might need to use a substitution to make it happen. Alright, so that concludes this video and the second video on our topic for finding limits analytically. This is a long topic. There's a lot here, but we're going to need these limit techniques later on in the course once we learn how to build the derivative. Alright, have a great day.